Okay, so we're skipping section 3.8, going right into section 3.9. Title is Differentials. It's an application of the derivative. So we'll first talk about the definition of a differential right here. Then we'll talk about some of the applications of a differential. So before you start writing any of this on the definition, just write these objectives here. And need to bring up this other program for just a moment. Okay, so we've got this curve right here, and right now it's a parabola, but this applies to any kind of curve of any degree or any type of curve, even regardless of the type of function. But anyway, point C here is a point on the curve, and then I've got another point over here on the curve as well. And what we're interested in finding, as we change from point C over to this point here, we're interested in finding the change in y, or delta y. So what was the vertical change going from here up to here, or the change in function value? So if we calculated f of c and then calculated the function value at this point and took the difference, what would the difference of that be, or delta y? Depending on the complexity of the functions, and sometimes that proves to be a little difficult, finding delta x isn't that hard. If you know where point C is, and then here you just subtract two integers, that's not too bad, or two numerical values. So rather than finding delta y, which can sometimes be a little difficult, sometimes it's easier to consider the tangent line at point C. So I've got the tangent line right here. This line is tangent to the graph of point C. Okay, and then rather than saying delta x, down here I've got dx. dx and delta x, they're interchangeable. So as I move from this point along to here, that's dx, or that's the change in x, that's delta x. And then as I go from here up to here, notice I'm not going all the way up to the curve or to the function. I'm going from here to here. That's why this is a different color, blue or purple, whatever that is. But the length from here, which is the horizontal line containing C, up to here, that vertical change is f prime of C times dx. Now f prime of C, that's just the slope of this tangent line at point C, and then dx is just the distance from here to here. So if you take the slope, multiply it by dx, that'll give you this vertical distance right here. So now obviously this vertical distance right now is not the same as this vertical distance delta y. You can see they're quite different. From here to here is much smaller than from here to here. But as this point becomes closer and closer to point C, notice I've got some values over here. So dx, as that approaches 0, then delta y, which again was this vertical distance here, can be approximated using this vertical distance here. And you can see, let me move it back to where it was. You can see, so dx is about 1, delta y is 1.26, and this other vertical distance, f prime of c dx, is 0.7, so they're not real close to each other here. But as you watch dx or delta x, as those get smaller and smaller and smaller, approaching 0, then delta y gets closer and closer in value to this value here. So now we're at 0.28 and 0.22, much closer together. And see if I can get this even closer here. the smaller your dx or delta x value, the better approximation you get between delta y and f prime of c dx. And that's the idea behind a differential. Rather than trying to calculate the actual change in y, you calculate this value, which quite often proves to be a little bit easier. And depending on your delta x, if it's relatively small, these two can be good this value can be a good approximation of delta y. So that's basically the definition here, or the idea behind a differential. When delta x or dx is small enough, then the change in y, or delta y, can be approximated using this. Delta y is approximately f prime of c dx. And this value dx, or delta x, the change in x, that's called the differential of x. And then this expression right here, f prime of x dx, this is in general now, not at just any given point, at a specific point c, but at any point x along f of x. F prime of x dx can be denoted by dy. So let me go back. I'll come back to the screen in just a second, but let me go back to that graph I had up. So this distance right here is what they were talking about. From here to here, so we have f prime of c dx. That's just dy. So along this horizontal line we have dx, along this vertical line we have dy, which makes sense. The slope of a tangent line is f prime of x. But we've seen other notations for f prime of x. One of the notations was dy over dx. So if we have dy over dx, that's going to give us the slope of this tangent line, and the slope of the tangent line is given by the derivative f prime of x. So f prime of x dx is denoted by dy, and that's called the differential of y. So essentially the definition of differentials here that we're using is that dy is equal to f prime of x dx. Dx is the change in x. Dy is approximately the change in y right here. So just a quick illustration here of how this can work. Here's an example. So let y equal x squared. Find dy, so we're going to use this formula right here. Find dy when x is equal to 1 and dx is 0.01. So we've got y equals x squared, but y is just equal to f of x, so y equal f of x, it's equal to x squared. So f prime of x, it's a pretty easy derivative, it's just 2x. So using this formula right here, dy is equal to f prime of x times dx. Well, f prime of x is 2x dx. Okay. Now we can plug in some known values. X is equal to 1. Dx is equal to 0.01. So that's a pretty easy calculation. It's equal to 0.02. You can just do that on a calculator. Okay. So compare this value with delta y for the same x value. And again, delta x, remember delta x here is just the same as dx. So now we're calculating the actual change in y. So delta y is the actual change in y. Remember, dy is an approximate change. So just let me go back for just a second here. X equals 1 and dx equals 0.01. Dx, remember, is a change in x. So we started with an x value of 1, and then we're changing that by 0.01. So our new x value, if we want to call this like x1, then x2 will be 1.01 because we're changing x by 0.01. So what we do now to find delta y is we take the difference of the function values at our two different x values. So the change in y, or delta y, could be thought of as just f of x2 minus f of x1. It's kind of like finding slope, change in y over change in x. Change in y is f of x2 minus f of x1. Okay, x1 is the function of the x value you start with. x2 is a new x value given your change in x. So this would be, the function is x squared, so this will be 1.01 squared minus just plain f of x, which is 1 squared. So in a calculator here, I have 1.01 squared minus 1 squared, which is 1, and it's 0.0201. So you can see the dy, the approximate 0.02, is pretty close to the actual change in y, 0.0201. Now you notice that there is, I mean, they're not exactly the same. There's a slight difference, 0.02 and 0.0201. So if this value is used as an approximation rather than the actual value, then there's going to be a certain amount of error in your calculations to a certain degree. So finding out what that percent is, the percent of error, or how far off, I guess, you are by using the approximation at the end. That's called error propagation. Okay, so if you let x represent the measured value of a variable and let x plus delta x represent the exact value so if x plus delta x is an exact value and you measure a value and let that equal x, then delta x is the error in measurement. So rather than using x plus delta x, the exact value, if you use the measured value, x, so if the measured value x is used to compute another value f of x. So if you take your measured value x, plug it into some function, and calculate that value f of x, the difference between the actual value f of x plus delta x and f of x, your measured value, the difference is called the propagated error. So notice we're taking a difference. So we have f of x plus delta x. We're subtracting f of x. F of this value and f of that value, these are function values. So if you're taking the difference of function values, remember function values are the same as y values. So this represents a change in y or delta y. So this right here, that's the propagated error. Okay. So another example here. The measured radius of a ball bearing so they have some kind of an instrument that can measure the radius or the diameter of a ball bearing. You just cut that in half, that would be the radius. But the measured radius of a ball bearing is 7/10 of an inch, so 0.7 inches. And the measurement is correct within a tenth of an inch. So plus or minus 1/10 of an inch, whatever instrument they're using to measure the radius, it's correct within a tenth. So if we're going to use the measured radius in another formula, let's say we wanted to calculate the surface area or the volume, if we're going to use the measured radius of 7/10 of an inch rather than the actual measurement, which, because 7/10 is correct within a certain 0.1. So find the propagated error in the volume of the ball bearing. So the volume of a sphere is 4/3 pi r cubed. Now the propagated error is delta y. But remember what we just talked about a little while ago. So delta v can be approximated by dv. I showed you a little bit earlier that, remember, delta y can be approximated by dy. So finding the change in volume, if you were to use 0.7, the measured radius, rather than the actual, whatever the actual radius is, that's a propagated area. That's delta v. We can approximate the propagated error using dv rather than delta v. And remember over here that dy was equal to f prime of x dx. So dv, if we wanted to find the derivative here, you're going to drop down to 3 and reduce this power, so it's going to be power of 2. So this is going to equal 4 pi r squared, but remember the differential, we have to multiply it. Over here it was dx, we're not using x, we're using r, so this is going to be 4 pi r squared dr. Remember remember over here dx is a change in x, so dr is going to be a change in the radius. Well, what is the change in the radius? You have to look back up here. The measured radius is 0.7, but that is correct to within 0.10 of an inch. So the change in radius could be within 1/10 of an inch, plus or minus 1/10 of an inch. And so the values we have here is the measured value of the radius is 0.7, but dr is plus or minus 0.1, because the radius can vary by 1/10 of an inch. So using these values here, we have 4 pi times 0.7 squared multiplied by plus or minus 0.1. So we have 4 pi times 0.7 squared times plus or minus 0.1. So if we were to plug that into a calculator, it's approximately 0.0 plus or minus 0.06158. So you would say the volume has a propagated error of about 0.06. What this means is the volume that you calculate using 0.7 could vary between the actual volume by about 0.06. Because remember, we're using a measured value of 0.7, which may not be the exact radius of the ball bearing. So just kind of extending this problem here a little bit. Talk about the ratio dV over V. So dV, remember that was 4 pi r squared dr. The volume of a sphere is 4/3 pi r cubed. So we're dividing by 4/3. Dividing by 4/3 is the same as multiplying by 3/4. So if you multiply by 3/4, here the 4's would cancel. So you just have the 3 up here. Pi's are gone. R squared over r cubed. That just leaves a single r in the denominator. So what that turns into, I know I got kind of messy, but what that turned into is 3 over r times dr. So for the problem we are looking at here, this would be 3 times plus or minus 0.01. That was dr, or the change in the radius. And the measured radius was 0.7. So that turned out to be plus or minus 0.0429. This is called the percentage of the error. So up here, the propagated area was about 0.06. That means the volume varied by about 0.06 from the actual volume. The percentage, that this right here would be the percentage of the error. So it's about 4.29%. So in your homework and on the exam review and on the exam itself, it's going to ask for the propagated error. And then it's going to ask for the percent of the error. That's what this is right here. So another application here of differentials is approximating function values So let's say we're asked to find the value of a function at x plus delta x. me go back to this graph we saw right at the beginning. So right where my mouse is right now, this is the x-axis. Okay? And let's say instead of point C, let's just call this x. Okay? So from here to here, that vertical distance would just be f of x. Okay? Now, if I travel along the x-axis by a value of delta x, so if I go from this x value over to this x value, that would be change in x, that's delta x. So this right now is x plus delta x. This function value up here then would be f of x plus delta x. And let me go over that one more time. So instead of C, I'm calling this point x. The distance this point is above the x-axis, that vertical distance is just f of x. And now how far above the x-axis is this point right here? Well, if I've traveled from here to here horizontally, that's delta x. So right now I'm at x plus delta x. So the vertical distance this point is above the x-axis is f of x plus delta x. Okay? But we've seen that could be approximated. This distance here can be approximated by this distance right here, this one in blue or purple, whatever that is, if delta x is relatively small. And remember, this is dy. So this dy plus this distance here, this little distance, which is the same as this distance over here, that's dx. But that's f of x. So f of x plus dy can be used to approximate this whole distance right here. Okay? So f of x plus delta x can be approximated by f of x plus dy. But remember, dy can be written a different way, so that can be approximated by f of x plus f prime of x dx. So an example here. This probably doesn't make any sense until you see an example of how this could be used. So approximate the square root of 16.5 using differentials. So the key here to using differentials is to choose delta x values that make your calculations easier. So if you look at the 16.5, taking the square root of that by hand can be pretty tricky. But if it was just the square root of 16, that by hand is really easy. Square root of 16 is 4. So if we want to split this value into something like this, then we would say x is 16 and delta x is 0.5. That's what it means by choosing values of x and delta x that make your calculations easier. So we can think about this as the square root of 16 plus 0.5. So then this here would be like x, and this would be delta x. So we can use the formula here, f of x plus f prime of x dx. So the function we're using is a square root function. So f of x is just going to be the square root of x. And so if, let me do this over here, if f of x is equal to the square root of x, then f prime of x, you got to figure out the derivative of the square root of x. So I'm going to rewrite this over here, x to the 1/2. So the derivative would be 1/2 x to the negative 1/2. That's just 1 over 2 times the square root of x. Excuse me. So then back over to here, f prime of x is 1 over 2 root x dx. Remember dx and delta x, I apologize, these are used interchangeably. Delta x, dx, they mean the same thing. So dx is 0.5, x is 16. So we're going to have the square root of 16 plus 1 over 2 times the square root of 16 multiplied by 0.5. Square root of 16 is 4. 1 over 2 times square root of 16 is 1/8 times 1/2. So this is 4 plus 1/16. So combine this. Just adding fractions like you do, it's no big deal. Multiply this by 16 over 16. 16 times 4 is 64. So this is 64 sixteenths. So this is 65 sixteenths. So on a calculator here, 65 sixteenths is 4.0625. Now what you gotta remember is these are approximations. Up here, f of x plus delta x can be approximated by this function, or this formula, f of x plus f prime of x dx. So we've approximated it as 4.0625. If we were to go to the calculator and find the actual square root of 16.5, it's 4.06201, so it's pretty dang close. But you can see that would have been pretty tricky to do by hand, coming up with this by hand. Using this approximation and differentials, we can get pretty dang close. So that's 3.9. Do the homework. You'll get more practice with problems like this on the review. Okay.